Hello and welcome to another video from the Power Piece series from movingelectrons.com. Our topic for today is going to be grounding. This is a video that's different from the ones we've done earlier in the sense the other ones have always been numerical problems and this one is more of a conceptual question. So let's get right into the problem. Which of the following grounding schemes will limit the phase to ground current in the system to be between 5 and 10 amps? And the options we've been given are high resistance grounding system, an ungrounded system, a solidly grounded system, and a low resistance grounding system. So, to know the answer for this, we need to know what each of these schemes is all about. So, what I'm going to do is we're going to do a quick primer on grounding, and hopefully that will give us an answer as we're learning about the different grounding schemes that exist and what grounding in power systems is all about. So, let's kind of begin by saying we have grounding right at the top, and that's divided primarily into two parts. What you have is you have system grounding and then you have equipment grounding. So you have system grounding, system grounding, and you have equipment grounding, equipment grounding. System grounding is used to protect the equipment. So don't let the names confuse you. Equipment grounding is not used to protect the equipment, it's actually the system grounding. Equipment grounding is used to protect personnel. So it's for human protection, whereas this is for the equipment protection. Also, system grounding is where the earth is connected to current carrying paths. For example, the neutral of a transformer. Whereas here the earth is connected to non current carrying paths such as the frame of a motor. So, for example, the of frame of a motor. So, when the frame of a motor is connected, that is generally used to connect to provide equipment grounding, right? Whereas when the neutral of an equipment is connected, that's to provide the system grounding. Our question for today primarily concerns about schemes related to the system grounding. So let us further expand this portion of the system grounding. System grounding can be divided primarily, most common system grounding schemes, there are four of them, and I will list them here and then we'll expound upon each of them. So you have your ungrounded systems, you have your solidly grounded systems, you have resistance grounded systems, grounded systems, and you have reactance grounded systems. These are the four primary schemes used for system grounding. So, an ungrounded system is this, where the neutral is not connected to the earth at all. A solidly grounded system is here, where the neutral is connected directly to the earth. A resistance grounded system is such where the neutral would be connected through a resistance to the earth. And a reactance grounded system, as the name suggests, would be through a reactance to the earth. Let's look at each of them individually now. So an ungrounded system is where there is no intentional connection to earth. So as you see here, there's no intentional connection to earth. Some of the advantages of this scheme are that you have continued operation during a line to ground fault. So your operation will not be disturbed even if you get a line to ground fault downstream. The disadvantage is that you have no control, or there's lack of control on transient overvoltages. You have difficulty in difficult to locate a line to ground fault. While these schemes were very common in the 50s and the 60s, they are rarely used today. Then you come to your solidly grounded systems. So your solidly grounded systems, there is an intentional connection to ground, but with no impedance. So there's no impedance in this connection. The advantage of this is that you have much better control on your transient over voltages. It is easy to locate a line to ground fault, and you can feed single phase loads. The disadvantages, on the other hand, are that the line to ground fault currents are very high. Can be 10 to 20k depending on the system that you have. That also, this kind of a system also has the possibility of very high possibility of arc flash hazards. And can lead to unplanned interruptions. Because what will happen is, if there is a line to ground fault, the phase on which the line to ground fault is there, that will um, you will lose that phase in a solidly grounded system. We'll come back to resistance grounded, so we'll go now to reactance grounded. Reactance grounded systems, so they will employ a reactance between the neutral and earth connection. So that's what we showed up here. There is a reactance between the neutral and the earth connection. These are rarely used, um, and a resistance grounded system which we'll now discuss, has a lot more advantages. System has more advantages. So this reactance ground system is not really used a whole lot, so we won't really go into the details of that. Solidly grounded systems, what I forgot to mention, is probably the most commonly used commonly used scheme in commercial systems today. Resistance grounded schemes, they will employ a resistance, as the name suggests, between neutral and earth connection, as we've shown here, right? The resistance grounded system can further be divided actually into a high resistance grounded system or a low resistance grounded system. So, a high resistance grounded system is used mostly for systems that are 5 kV and below, whereas a low resistance ground system is used for systems that are mostly 5 kV to 15 kV systems. In a high resistance grounded system, when you're following this scheme, the fault current is limited. Line to ground fault current to between 5 and 10 amps. In this case, line to ground fault currents can be between 400 to 2000 amps. In a high resistance ground system, as you can imagine, as the name says, there's a high resistance here that's used, and therefore the amount of fault current that's flowing into the system is limited. Whereas in a low resistance grounded system, this is a low resistance, therefore the fault current that's flowing into the system is higher. Now, the high resistance ground system provides the advantage of an ungrounded system. Advantages of ungrounded systems, in the sense that uh, your system can continue to operate in the case of a single line to ground fault, with added benefit of better control on transient overvoltages. And the ground fault basically may be left on the system for longer. So once now that we know a little bit behind all of these schemes, if we go back to the question and look at it again, what we've been asked is which of the following grounding schemes will limit the phase to ground current in the system to between 5 and 10 amps. So we know in an ungrounded system that's not true, because really you're not limiting the current at all. There's no current flowing into the system. In a solidly grounded system, you don't limit the current, you'll get very high currents. In a low resistance grounded system, we've seen the currents can be between 400 and 2000 amps. So the right answer, as we've seen, is the high resistance grounding system, where you have a high resistance value here between a neutral and your earth connection, and you're limiting the current to most values being between 5 and 10 amps. So I hope that gave a good uh, introduction to grounding schemes in power systems. Of course, this is a very detailed topic, and each of these have their own protection schemes, and have their own advantages based on what the system is like. So in future videos, I'll go in those details. I'm hoping to get a chance to address each of these individually. What I'll leave you with today, again, because this is not a numerical problem, there's no sample problem as such. What I'll leave you with is I'll encourage you to read up on equipment grounding. So what we did today was a brief introduction um, on system grounding. So I'll encourage you to go ahead and read up on equipment grounding. You can do a quick Google search and you'll get a lot of documentation. So just at least get a good primer, a good introduction of what it is, what equipment grounding involves, and hopefully in the future I'll do a video on that topic as well. So I'd love to hear your feedback on today's problem, just because it was very different from what we've done earlier. This wasn't a numerical problem. I'd like to hear your feedback as to if you enjoyed a video of this type, and we could do a good mix of numerical and conceptual problems depending on the feedback that I receive. So you can send me an email at nimish@movingelectrons.com or leave your feedback in the comment section below, and do subscribe to the channel if you haven't already done so. All right, till next time, take care and have fun.